going through and looking at this, okay, I would highly recommend you go through and look at these reagents. I told you to do this last week. You should go through and look at each reagent and kind of classify them as to those categories. These categories, for sure, I will test you on. I have a test question that is based off of this right now, okay, and it will show up. So given those reagents, where do they classify? Would we expect them to be in a 3-member transition or a 4-member transition? Okay. Why do we know those differentiations? The 3-member have stable leaving groups. The 4-member have horrible leaving groups. Should we look at a couple? Yes. Okay. BR2, I think, is one we did last time. Let's take a look at the MCPBA. And as I'm drawing this, I feel like I already drew this one here. But here's our MCPBA. The weakest bond in that connection is the oxygen-oxygen bond. Okay. That bond isn't as nonpolar as we would expect for 2 oxygens. And it's not nonpolar because if those electrons go this direction, what would we result in? A resonance-stabilized carbanion, or not carbanion, a resonance-stabilized anion. That resonance stabilization means what about the leaving group? It's a good leaving group. It's a stable structure. What happens to the other oxygen if those electrons shift that way? If those electrons in that bond go towards the left oxygen, what happens to our soon-to-be purple oxygen? It's going to be positively charged. Okay? Because it is positively charged, it is a good electrophile. Okay? If we appropriately drew out the Lewis structure, what is missing from our Lewis structure? The electrons. If we add in our lone pair electrons, does that oxygen have lone pair electrons? Yep, which means it can act as a nucleophile. So that oxygen atom will act as a Lewis acid and as a nucleophile. We have a great leaving group. MCPBA, as far as its chemistry, fits in the 3-member transitions, okay, or intermediates. What's the product of the MCPBA? An epoxide. Okay? So if you can come up with ways to classify and think about how those reagents work, you can start to draw conclusions about where they're going to go. If you choose to not do that, that is perfectly acceptable. You will miss one question, and maybe not even that. Okay? But what you'll have to do is memorize what each of those reagents do. Okay? How many of you have memorized each of those reagents? Okay? So that's the balance. Okay? We will have to memorize some, but memorizing all can be a big challenge. Okay? Ultimately, the way you would expect to see that, which is actually going to be the next slide, some of these reactions are going to require some oxidation reactions afterwards. Okay? So when we run an electrophilic addition, we might add something weird to the structure. Okay, what do we mean by weird? Well, it's organic chemistry. What would not be weird? Carbon and hydrogen. Okay, what other atoms have we seen very commonly? Oxygen, nitrogen. Bromine, fluorine, all of our halogens. Okay? Those of you that had me in first semester, we started Unit 1 with a periodic table. And what did I do to the periodic table? I deleted 3/4 of it. Okay? Because organic chemistry isn't concerned, for the most part, about most of the periodic table. We keep our focus down to 10. So if we're encountering elements that aren't part of that 10, guess what? Those are weird. How do I get rid of them? Okay? So the big examples that I gave, boron, mercury, osmium, manganese. Okay? Those are all things that we don't want attached to our structure. They're going to require an extra step to remove them. Sometimes that extra step is implied in the case of the osmium. Sometimes it's an extra reagent sequence. Okay? So if we go through and look, if I do an addition with boron, how do I get the boron off of the structure? Well, how did I get the boron on the structure? Okay? To get the boron on the structure, I had to do an electrophilic addition. And we're correct. BH3 is a big tip-off that we're doing that. What did I add BH3 to? An alkene. So remove the boron, make it a pi bond. Now we have our starting alkene. Okay? BH3, just because it's obnoxious and sometimes we can see it, can be written as BH3, can be written as BH3.THF. Boron is not a stable substance, okay, or borane, and so it coordinates to the solvent. The solvent is THF. Okay? The dot is just saying it's there to stabilize it. Okay? And it's more than just adding the solvent. That's why we need the dot. Okay? To be extra obnoxious, we could also write it B2H6. Why? Because we hate you. That's just what boron does. It's unstable. So if we're going to buy that boron reagent, it's probably dimerized, and that's how it comes out. Okay? Ultimately, what you're seeing is boron with hydrogen. Okay? And boron in a way that has an empty p orbital. Why an empty p orbital? It only has 3 bonds, so it has 6 electrons. Why do I need that empty p orbital? What am I going to do with it? Fill it with electrons from the pi bond in an addition reaction. Okay, what type of addition? What are we adding? What is boron acting as? An electrophile. So what type of addition? Electrophilic addition. That's where all the terms are coming from. It's referencing each of the individual pieces that went into it. Okay? We now added H and the boron across the pi bond. We end up with that weird structure with the boron on it. I don't want the boron on it, so what do I have to do? Some kind of fancy redox chemistry. Okay? The redox mechanism you're not responsible for. If you want to, you can talk to me after class and we can discuss that. But ultimately what happens is the hydroxide replaces the boron. The fancy replacement, it does retention of stereochemistry. Okay? So that would be the complex aspect behind that. How would you be able to predict that stereochemistry? Remember, I classified the reagents according to syn or anti-additions. I didn't classify them according to that. I classified them as 3-membered or 4-membered. Guess what the 3-membered do? Anti. What did the 4-membered do? Syn. If you know those shapes, you know those chemistries, you don't have to memorize an extra term. Is it easier to memorize the term? That's entirely up to you. Okay? So, end result. Ta-da! That was it. Okay? Next one. Okay, one of the reagents adds mercury. Okay, mercury and OH across a pi bond. Okay, do I like mercury? No, so I need some weird redox chemistry. Weird redox chemistry in this case? No, not boron. It's hydride. Okay, this is distinctly different from from boron because I'm looking at BH4. Does the boron have just 6 electrons around it? No, it has 8. Formally, boron is negative. The boron is negative because there's too many electrons in it. It can't accept more. It can't really get rid of those. So what ends up happening is a hydride takes the electrons away and ejects the mercury. Okay? So recognizing some of those patterns. Yes, zeroing on elements is phenomenal, but you also have to look at the surrounding environment. Okay? Osmium. Okay? With the osmium one, the leaving group in the osmium case, if we draw out that result real quickly. That osmium wants electrons. It starts to steal them from an oxygen. Oxygen's unhappy, so what happens? The pi bond shares out. What is the leaving group, if you will, in this? Electrons, which are not stable. So what happens? It immediately reacts back, and we're in that four-membered transition. What are the four members?
5.
Waiting for that. It's not 4, it's 5. 2, 3, 4, 5. Okay. If we look back at how I reference them, it's 4 plus. Okay. The result is we end up with this goofy-looking structure known as an osmate ester. We have a carbonyl, or sort of a carbonyl, okay, with that ester kind of functionality, except it's osmium instead of carbon. So we call it an osmate ester. That structure is not good. I don't want osmium connected to it. I would love to say there's a clear second step. There isn't. Okay? Sometimes it just shows OSO4. Sometimes it says OSO4 and water. Sometimes it says OSO4 and HSO3 minus. Okay? When it comes to osmium, to cleave it, something else is happening. You're not responsible for that mechanism. You are responsible for knowing that it happens. Okay? In that cleavage, what's happening? We eject those groups and we replace them with OH. Okay? And we get our diol. Where would I expect those alcohols? Should they be on the same side or opposite sides?
The same side.
Same side. Why? We had that 4 plus membered ring. So if we understand the chemistry that got us there, we can predict their orientations. Okay? The permanganate does the exact same thing, okay, as the osmium. They have the same basic structure. It's the same basic pieces of leaving group. Okay? The secondary reaction, depending on the conditions, can go all sorts of haywire. We can just do diols, or we could split out into the carbonyls. How do we know? What's that? I would have to look at the reagent conditions, and in particular, the reagent conditions I'm looking for to go to the carbonyl. Heat, okay, and concentrated permanganate. If it's cold, it doesn't go as far. Okay, we've got a nice little hint up here. We're oxidizing. Which one did more chemistry? The osmium case, more oxygen, or the permanganate case? The permanganate did more oxygen. So to get more things to happen, what do I need? More energy. Okay, I need more heat. Okay?
Do these things ever take off?
Like explode?
Well, no. But I mean, like, get enough heat from one reaction where it's going to start to trigger another reaction?
They can. They absolutely can, and that's usually a scale issue. In an undergraduate lab, typically not. Okay? What's happening here?
Peroxide ring.
It's not even a peroxide ring. This is the ozone reaction. It goes through a malozanide, and it does all sorts of weird, crazy stuff. Okay, remember how I said there's some things you should just memorize? Ozone's one of them. You should just memorize the ozone. Okay? The ozone is very conditional on that second step. If you provide a reducing oxidizing agent, it doesn't oxidize all the way. If you just let it go, it oxidizes all the way. Okay, what do I mean? Okay. Pseudo-mechanistically, what can happen? Let's see, one of those oxygens, let's say that one, gets greedy and steals, not that one. Let's say this one steals electrons, okay? Which then means that carbon has exceeded its octet. So what happens? Oh, I didn't draw it in the nice spot. That's fantastic. We eject this piece. Oh, God, yeah. Freaking hate malosonide. It goes through some very interesting intramolecular electric cyclization reactions that happen very, very fast that eventually take you to this structure. Once we're at this structure, now the stuff that I was thinking about is going to happen. This oxygen up here, losing electrons, eventually gets greedy enough that it steals them. That carbon has now exceeded its octet. What happens? It can shuttle electrons around. Okay? That thing can end up cleaving open. And of course, I probably drew the arrows wrong. And you could end up with, yeah, I've lost carbons. The acid and a carbonyl. Okay? If that carbonyl has hydrogens on it, it can be oxidized more. Okay? If it does not have oxygens on or hydrogens on it, it can't be oxidized anymore and it stops. Those conditions are what get dictated in that second step. We would either say usually DMS or pretty much anything else. H2O, H2O2. What is DMS? Dimethyl sulfide. How many oxygens are in that? None. What's its job? To scavenge oxygens. So we end up not oxidizing as much because the DMS takes the oxygens instead of the carbon reagent. Okay? So, and of course, there I show it. So, take a swing at some of these. Give you 3 or 4 minutes. Okay? If you've got questions, raise your hand. A lot of these have different little nuances that you should be thinking about and considering when you draw out the products. Okay? So take an attempt. First one. Couple things I want to address. If we go through and take a look at the work, we've got the starting materials written out. That is useful to go through and write out an example like this because you don't have it in your notes. But wait, didn't somebody already give you the slides? So do you already have it? Did you just waste time writing out the reaction? Yes. Okay. Just be aware of that. Okay. Next part that I got was, well, I don't really know how it works, but I think I've got an answer. Cool, that's fine. I drew a quick answer out, and then we talked about, okay, well, why would you do that? Okay. If you don't have a good answer for why, and you got nothing else, run with your instinct and run with it. Okay? But we pushed it a little bit further and said, well, the bromine would react with the pi bond. Okay? It would then need to form some kind of 3-membered ring. Why would it be forming some sort of 3-membered ring?
To stabilize both carbons.
That bromine is a good leaving group. It fits the 3-membered ring pattern. Okay? That 3-membered ring becomes useful because then he says, okay, well, the positive bromine, okay, I don't want. That's bad. So what has to happen? The other bromide must come in and attack. Fantastic. Scribbled out. A little bit irritated you scribbled it out, but thank you. The scribbled out version shows the bromines at the exact same carbon. If that bromine comes in as a backside, what happens? We're going to eject the bromine bond. The bromines will be connected to 2 different carbons. Right? So that got fixed. We then run into the issue of showing them both wedged. Well, if it's coming in from the back side and I'm showing that, should they be on the same side? Nope. They need to be on opposite sides. This is one of the problems with pen. I use pen when I go through and do it too. Okay, and I'll do the same thing, cross things out. Okay, it can be difficult to see if you're switching from wedges to dashes. So just be aware of that. That was fixed. Okay, they're trying to show the dash there. Does that make sense? Okay, so we're trying to piece things together. Is there another way? Come on, that we could pull this off? Yes. Okay, I could look at this and say, okay, this must be in. Or I could have just memorized. Br2 adds bromine. Okay, across a pi bond. What is different about what I've drawn as opposed to what was up there? Stereochemistry. Do I need to worry about stereochemistry?
No.
Are those stereocenters?
Yes.
Yes. Do I need to worry about stereochemistry? Okay. In this question where it's just an open, just provide an answer, yes. Yes, you do. Okay? You could decide that is too difficult and I don't want to do that. That is fine. You've at least acknowledged that you understand it's an electrophilic addition where the bromines go to different carbons. Phenomenal. You get points. You just don't get all of the points. Make sense? Yes.
Could you just say the anti-addition on this one, anti-addition of bromines? Because you're going to get two.
So that would then be the next layer. You could say, okay, well, what is that stereochemistry? You could memorize anti-addition. If you memorize anti-addition on top of that, you would then know you need the wedge dash. Make sense? Okay. You also have to realize
There's going to be two products.
there's two products. Okay. We could have formed the the bromine three-membered ring above or below. If you just memorize the anti-addition, you tend to only see one answer. So you'd have to memorize that this adds two bromines. You have to memorize that it's anti-addition. You have to memorize that you have the potential for two products. That's one reaction. None of that memorization applies to anything else. That's where I run into issues with memorization. Okay? Add to that, when are you going to forget that content?
When you need the most of it.
Probably at best when you walk out of the classroom. Okay? That's not useful. What I do want you to think about is how those pieces fit together and how we can classify them so that we can come to broader conclusions without having to memorize all the reagents. Because none of you, I believe we established, are synthetic chemists. Make sense? Okay. That's my choice. Doesn't have to be yours. You can just brute strength memorize. Okay? Let's see, was I nice enough to provide answers for these? Cool, I did. Okay? You notice when I drew it out? Oh, you screwed it up because I didn't show wedges and dashes. You're right. I was lazy. Okay? Maybe the question didn't ask for it. How would I know? How would I know if the question was asking me to show all those wedges and dashes?
It asked you to show stereochemistry.
It could ask you to show stereochemistry. Okay? Most of the exam is multiple choice. In this kind of question, this is a multiple choice question. This isn't asking you to think at all. It's just, do you know the answer? Okay? So based off of the multiple choice answers, you would be able to say, I need to show it. Why?
Because it will be there.
You will see the wedges and dashes in your multiple choice answers. Okay? So you don't always get pushed at it. So don't stress a lot about it. Okay? The mercury reagent, okay, it adds H and OH. It adds it across the pi bond and it adds it in the normal fashion. There's our H and our OH. We talked about another reagent that does this exact same reaction. What is that other reagent? Exactly. H plus and H2O. Acid addition of water. Does the exact same thing as mercury. Well, if it does the exact same thing, why do I need two different reagents?
Rearrangement.
The H plus and H2O, if we think back to the acid addition mechanisms, generates carbocations. Guess what the mercury reagent does not create? A carbocation. What does it form? A three-member transition that prevents the carbocation formation. Because there's no carbocation formation, there's no rearrangement. The acid addition, because it forms a carbocation, has the potential for rearrangement. Would this one have rearranged? No. You should be able to go through and solve that. You'd be forming a tertiary carbocation. There's no reason you would rearrange. Okay? So which of these two reagents should you use? The mercury one or H plus and H2O?
H plus H2O.
You should use H plus and H2O. Why? Mercury is death. Okay? If I don't need to use a dangerous reagent, don't use it. That concept is known as? Common sense is an interesting phrasing on that one.
Common sense is not a common.
It actually has a distinct field. Subtle hint.
Safety Society? Green chemistry.
It is green chemistry. Green chemistry is about minimal exposure to chemicals. Okay? Both by amounts and hazards. Okay? So you can see questions about green chemistry. It's becoming increasingly more popular. Ultimately, all it is don't do stupid stuff. Okay? But it requires a secondary lens through looking at the material. Okay? If we move to the bottom one, that one's extra tricky. You're going through a carbene intermediate. Okay? ACS sometimes likes to test on it, sometimes not. I don't like to reference it because none of my training dealt with carbene chemistry. Okay? It tends to be a smaller field. Why is it a smaller field? Carbene, well, it forms these cyclopropyl structures, which are really small, okay? And those are now all nonpolar bonds. So as a structure, the cyclopropane is actually pretty stable, okay? Or surprisingly stable. So it limits chemistry. What's the other carbene chemistry? Does it look familiar to anybody?
Yeah.
Known as?
Azide?
Close. Diazo methyl. Okay. Diazomethane. Why is that so dangerous? That nitrogen really wants to come off the structure. It literally is explosive. People that work with that material regularly are missing fingers. Okay. That's how dangerous the chemistry is. Okay. In grad school, I was supposed to run a reaction using diazomethane. Like that was one of the suggestions. The advisor said no. And I started talking, I was like, I don't know else how to do it. And so I started talking to some highly skilled synthetic chemists. And they're like, well, I'll talk to them because I can do it. Like, that's not a big deal. And they volunteered, and the advisor still said no. Okay? So highly skilled chemists avoid the reaction. Okay? As we continue around the ring, the permanganate gets fun. This gets our concentrated and hot. You oxidize the crap out of it. Okay? Those of you that haven't had me, what's your shortcut? Have you heard of a shortcut for this?
Yeah, right.
Yeah, right? Yes, there's a shortcut.
I think I remember it.
Stretch the double bond,
Cut it in half. Yeah, that's what.
and then cut it in half. Of course, there's a structure underneath it. And replace it with oxygens. Okay? The other double bond, stretch it. Is there more stuff underneath it? Cut it in half, replace it with oxygens. Okay? That pretty much solves it. I did make a goof up here. When we go through and do it, it's such a strong oxidizing agent that what does it do? It continues to oxidize. So it'll turn that hydrogen into another oxygen. There's that acid. Where's the typo? Those also have hydrogens, which means So oxidative cleavage, you can just stretch, drop on your oxygens.
So won't the other two also have oxygens too? Or is that just two credits?
So other two, look at the other two carbons. We'll highlight those if you come back and review it. Those green carbons.
No, not those two. The two.
Those ones that have, like,
No, there's. You can't add on the single bond.
true, can't add to the single bond. What we're doing is oxidative cleavage of alkenes, non-polar pi bonds. That's what we're reacting. How about those green carbons? Well, we already did that one. How about the other green carbon? Can we oxidize that one further?
No.
There's no other hydrogen there. We have to have that hydrogen to oxidize further. It's only connected out to carbons. So?
The answer print, over there as well?
Yeah, you have to make those OHs. Which sometimes I do that intentionally to start the conversation, but I honestly can't remember with that one. Okay. Next one, our BH3 and THF. What is it adding? OH and H, just like the mercury. Except how does it do it differently? Okay. Notice we have stereochemistry here. The boron 1, the stereochemistry is a little bit more straightforward. You are expected to know stereochemistry for the boron 1. It is not anti, actually. It's a syn addition. You might be saying anti because the methyl. Well, dashed and wedged, isn't that anti? What was added? Hydrogen and OH. If the methyl is dashed, what's the hydrogen? Wedged. If we take a look at the two things that were added, they were added on the same side of the pi bond. That was a syn addition. Okay? The other part that can become confusing, this is why I don't recommend memorization. It added the H to the more substituted position as opposed to the least substituted positions. So this would be known as anti-Markovnikov. What was the addition? A syn addition. We have anti-Markovnikov and syn. Wait, what? How is it anti and syn? Two different things. Okay? That's why I don't recommend the memorization. There's too many layers of stuff the terms crossbreed. Okay? Plus the enantiomer. Okay? We get two potential products coming out of all electrophilic additions. Last one, MCPBA. We form the epoxide. So there we go. We get the epoxide. Anybody notice anything problematic with our epoxide? As a hint. Those are chiral atoms, which means we might need to be careful about stereochemistry. Yes, we do need to be careful about stereochemistry. Well, since it's all happening on the same side, it must be a syn addition, right? It is still a syn addition.
Well, it's a syn addition, but you're not going to get.
The methyl's position has nothing to do with the addition. It has to do with where they started. They started trans to each other, which means in the answer they must be trans to each other. Okay, plus our enantiomer, which in this case I think was a dumb statement to add because, no, never mind, it's valid. It's valid. It's not meso. Okay? Kind of makes sense?
Can you get that one if it's warm enough to start rotating? You have to worry
No.
about.
The epoxide all happens in one step. It won't rotate. Okay? Which gets us to chapter 10. Ultimately, chapter 10 is really just a review of substitution. It's just SN1, SN2, E1, E2. Okay? But we're now adding in some extra reagents. I went through and divided out the sections because while I agree with Carty's organization here, sort of, I don't agree with necessarily how he presents it. So I'm jumping around a little bit. So I look at it as let's make our leaving groups better. Okay? Then what happens with amines, because they just do weird stuff, and then let's look at better nucleophiles. Okay? That is our full division out. So if we start, one of the things that we need to remember is those factors that contribute to our substitution elimination. Nucleophile, base, substrate, solvent, heat. You have to have those things at the back of your mind, right, so that you can be able to classify these reactions. So, oxygen in our substitution eliminations. If we convert our standard substitution from an alkyl halide to an alcohol, now we have the OH. Why might the oxygen be synthetically useful? Those lone pairs can do what? We have electrons. What could we do with them? We could donate them. What could we donate them to? We could donate them to an electrophile. Okay, so a positively charged species. Why am I balking at the reference of a base? What would be the charge on a base? Negative. If they're donating to an electrophile, that can't possibly be a base. They could donate them to, H+, in which case the oxygen acted as a base. Okay, so you got the term, but your application is a little bit off. Okay, so it is synthetically useful. It can act as a base or nucleophile. Good. We aren't just saying the words that are down there. It reacts with an electrophile, so it is a nucleophile. Okay? If it was a halide, we don't have that chemistry because
they're negatively charged.
let's make it a halide. Whoops.
Oh wait, I thought you were talking about the nucleophiles.
Would I expect the chloride to share with a hydrogen?
No.
No. What's our reason?
It's a strong acid.
Forms a strong acid, so that's bad. There's another big reason. What did we do to that bond? Does the arrow show that bond doing anything? No. So for the lone pair on chloride to react with hydrogen, what has to happen? Chloride would need to become positively charged with two bonds. Do we allow halides to do that? No. Okay, so that doesn't fit our patterns. So we have new chemistry because of that. Okay, due to its electronegativity, what chemistry is available? If it is electronegative, what is it doing? Drawing in electrons from where? Anywhere you like. Common answer for electronegativity. It is also horribly wrong. Okay. Anywhere nearby, better, but not good enough. From a bond. Electronegativity is very specific. It is referencing the ability to remove electrons from a bond. Because oxygen is highly electronegative, what happens to the electrons in this bond? That red bond. They go to the oxygen, which means, what's the reactivity? The oxygen would become partially negative. What happens?
It becomes an acid.
H+ floats off, and I have an acid. Because of its electronegativity. What does it do to the carbon? Same thing. Makes it positive. So it makes it an acid? No. According to our definition system, it makes it an electrophile. Anybody seeing a problem with now looking at an alcohol functional group?
Yes.
Yes, it literally does all of our chemistry. Okay? So if I add it with another species, that alcohol could do so many different things that I will likely get a giant mess of products. So what might I try to do? Get rid of some of that chemistry. Limit it somehow. If I want the oxygen to act as a nucleophile or a base, what might I do to that hydrogen? Get rid of it. Because if the hydrogen is gone, guess what it can't act as anymore? an acid. And now it can only act as a base. So what we're talking about in this chapter is looking at any functional group and saying, well, what happens? What could it do? How could I tweak it? What are my options? Okay? You've seen alkyl halide chemistry. So the biggest thing that we could do to the alcohol functional group would be turn it into an alkyl halide. Make that a chlorine. Now all of that chemistry isn't available, and I can limit the chemistry of my structure. What's going to allow me to decide to do that? Well, what am I trying to make? Okay. For the sake of the class, you're going to be told, hey, make it an alkyl halide. Tell me what to do. Okay? So, make it an alkyl halide. Tell me what to do. That one wasn't rhetorical.
How to get there, is that what you're asking?
Make it an alkyl halide. In this case, make it an alkyl chloride. What needs to happen? I need the oxygen to leave the structure. Why would the electrons go towards the oxygen?
More electronegative.
Oxygen is more electronegative than the carbon. That's generating this polarity. That's why that carbon is partially positive. Fantastic. What else needs to happen?
You need to stabilize that oxygen when it leaves, because it's going to leave right now.
Right? So if we go through and say, well, let's just say it leaves. Well, what would it leave as?
OH minus.
OH minus. And what do I know about OH minus? That doesn't pass the face test. Okay? That hurts. Bad leaving group, which means
Finding the stabilizer.
your reaction sucks. Okay? I don't have a good leaving group. I need to make it good. How could I make it good?
You could change it.
Change it by.
Adding a hydrogen.
So the first thing that I'll do is put a hydrogen onto that structure. Like, that's what I want to do. How do I get that hydrogen onto that structure?
HCl.
What kind of reaction happened? I know it's crowded there at the bottom. What reaction happened there, that red arrow? What kind of reaction was that?
Hydration reaction?
No.
That was a base.
This is an acid-base reaction. Remember, we had those 5 classifications. Acid-base, substitution, radical, elimination, addition. If you can say, this is what I want to happen, well, what kind of reaction is that?
Acid-base.
Acid-base. What should I add?
Acid.
Acid. You now have a reagent. Okay? By saying, I want this to happen, can I make that happen? Yeah? Good. You now have a step. Whereas before, what was it? I just need to do that.
Magic.
Magic. Or I memorized that a reagent does this. Okay? They both work. It comes down to how good your memory is. So if you can start to say, what do I want to happen? You can start to figure out what pieces you need to add in. Okay? So I need to add an acid. What acid do I want to add?
HCl.
Why do I want to add HCl?
You want the chlorine?
What else needs to happen to go from here to here?
You gotta add the
I need a chloride. So just put it all in at the same time and just see what happens. It works, sort of. We'll address it in a second.
It's just not reversible.
Okay? No. The problem is it's too reversible. Right? So what we're coming up with is identifying those major players, what are those changes, and then saying, well, let's just start doing it. Oh, that was a mistake. I formed hydroxide. That's a bad leaving group. I know it has to leave. Let's make it a better leaving group. How do I make it a better leaving group? Turn it into
H3O plus.
water so that water can leave the structure. Water does pass the face test. Okay? Does that make sense? Those are the pieces we're trying to break down as we move through it. Right? So when we go through and look, Cardi starts with a bunch of reagents. What do all of these reagents have in common? They're all acids. Their sole purpose was to do what?
Turn an alcohol into an alkyl halide.
Make that a good leaving group. Once it's a good leaving group, then I can evaluate the rest of the chemistry. So there was a suggestion to make it an alkyl halide. Chlorine is a halide. Iodide's a halide. Bromide's a halide. This is an awesome suggestion. Oxygen is not a halide. And I've actually lost atoms from this structure. Okay, so it's not just make it an alkyl halide. It's recognize what the chemistry allows me to do. Okay? What is different about these two on the far right?
The first one didn't go to completion.
Nope, that's completion.
There wasn't enough H2SO4 to pump the hydrogen out.
So you're referencing that this is dilute and that's concentrated?
Yeah.
Okay. What does it mean if it's dilute?
It's mostly water.
Okay, it's mostly water. So there's a small amount of acid, which means what happens with that species? Only a small amount goes to form the good leaving group. Right? Well, now what happens? If we looked at these all had acids. What happened? The leaving group left. We form a carbocation, and then the halide comes in and attacks. Nucleophilic attack. What's our nucleophile? Sulfate. Awesome idea. Why are you saying it doesn't work? It's not sterics.
It's a stable leaving group.
It's a stable leaving group because resonance. Sulfate is an exceptionally stable leaving group. It is, or an exceptionally stable ion, which means not a nucleophile. Can't attack. Where's my nucleophile? What? Remember, only a small amount of this became this, which means what's left over? More alcohol. What did we say that oxygen could do?
Do everything.
It could do everything. It can act as a nucleophile. This is two equivalents. Okay? Why did that not happen in the bottom one? We use concentrated sulfuric acid, which means how much of the starting alcohol was there?
Zero.
0. There was no starting alcohol. There's no nucleophile. How would I stabilize that carbocation if I don't have a nucleophile? What do I need? Electrons. Where could I possibly get electrons? Of course, I drew it inverted. To stabilize that carbocation.
The CH bond and the next one.
In an elimination reaction. Okay? It's evaluating each of those pieces. This becomes challenging. You're responsible for knowing all of these things and then also being able to put them together. It's not just did I memorize one reagent in one step. Okay? And that's why students tend to struggle with synthesis as a field, because in synthesis you're given starting point A and starting an ending point F. You're like, I can go from A to B 20 different ways, but I can't make it to A to F. Why not? Because you don't acknowledge each of the individual steps in between. Each of those individual steps in between is exactly what we're trying to break down and work through. It is challenging. We'll get through it, but it's looking at those pieces and trying to identify what changed, how do I make that change? Make sense? Okay. So if we go through and look at a generic version of this, we could break the mechanism all the way down. When we go through and evaluate this, we see a branching here. What is that branching point referencing?
Two possible products.
Is it two possible products? Okay, let's look at the branch point, blue versus red. That's a carbocation. Carbocations aren't a product, so we'd have to continue that all the way down. It's two different mechanisms. One branch point, the red, has A minus attack at the exact same time as the leaving group leaves. We're still running a substitution, but that substitution is happening all at once. That's an SN2. The blue method forms a carbocation, and as soon as you see carbocation, you should be screaming unimolecular, not SN1 necessarily, but unimolecular, and you're like, I can't even say that. That's okay, just shout 1. Okay, SN1 or E1. Okay? When it comes to the reagents that we just discussed, they tend to follow the SN1 or the 1 path primarily, carbocations. Okay? There are exceptions. If you have a primary alcohol, you can make it react. It's not going to react under SN1 conditions. Why not? Primary carbocations are unstable. That mechanism switches to the SN2. So these reagents with alcohols will oscillate back and forth between SN1 and SN2, preferencing SS1 or preferring. Let's do preferring
I think you were
the
right.
1 type. I think preferencing was right. I think that worked. Okay? Kind of makes sense? All of these are substitutions so far. Well, where's the elimination? How would I get the elimination? What's the difference between SN1 and E1? Elimination versus substitution. E versus S. God, that was so obvious, but that's exactly what I asked. So that's awesome. It's fantastic. What else is different?
E1 usually means heat.
Conditions.
Just literally SN1, E1. Ones are the same. S's and E's are different.
You're either replacing something or leaving something.
There is a nucleophile.
N. N is different. What the hell is N? Nucleophile. Can iodine act as a nucleophile? Yes. What reaction are you going to get?
Substitution.
The one with the N. Is bromide a nucleophile? Which reaction are you going to get?
The one with the N.
The one with the... yeah, I walked into that. Chloride. Substitution. Sulfate.
Elimination.
Not a nucleophile. So I can't get substitution. That means elimination. Okay? That's the balance that you need to be considering. What is that other species? All of these are putting in that acid to get the or to make alcohol a good leaving group. Now it's what is that other piece? Is that other piece allowing me to do more chemistry, or do I got to do internal chemistry? Substitution versus elimination. Okay? Sorry, backtrack a lot. Balls. Oh, I killed it. Damn it. So the whole point of the zinc chloride acts as a Lewis acid catalyst, meaning it needs to accept electrons. It accepts electrons from the oxygen. We eject the chloride, and we end up forming this structure in between. This is a better leaving group than even water. Okay? So because I've now made an even better leaving group, chloride can come in and do its reaction. Okay? The primary reason we talk about this isn't so much as it's a new reagent and all that fun stuff, is it's an exceptionally fast reaction. Okay? It is so fast that it is typically put into a classification test. I have an unknown substance, I add zinc chloride and HCl to it, it becomes cloudy, and it's not even cloudy, it's turbid, is actually what it's referencing, okay, immediately. Okay, turbidity just means that we've got multiple phases. Well, what are the multiple phases? If I have an alcohol and I add an acid to it, both of those are water soluble. What is the product of this reaction? Whoa. An alkyl halide. Is an alkyl halide water soluble? So what happens?
It precipitates.
It either precipitates or it just separates out if it's still a liquid. Okay? That separation process causes it to look kind of foggy. Okay? That's the turbidity. So if I take a substance, I was like, I think this is an alcohol, and I add zinc chloride and HCl to it, and all of a sudden it becomes turbid. Cool. I'm right. It was an alcohol. But it happened fast. What mechanism did we say these reactions run by? SN1. Nice hedge. Okay? SN1. What substrate favors an SN1 mechanism?
Nucleophile?
Substrate.
SN1, carbocation.
Where would a carbocation be most stable?
What substrate, an acid?
With a tertiary alcohol. I don't know what you said, and I'm short on time, so I'm going to keep going. Sorry. So what we can do this for is we can say a student takes an unknown alcohol and mixes it with the Lucas reagent, and it instantly becomes turbid. Which of the following is a valid guess for the unknown compound?
Alcohol?
Okay. Alcohol. Yep, there's the key word. It's not just an alcohol, a tertiary alcohol. Okay? I'm not a fan of this kind of question because this is pretty much a raw memorization question. Okay? That said, classification tests as a whole are very common in organic chemistry. Okay? And in fact, in lab, we're going to do a lab where we just do a whole bunch of classification tests. Why were they so common in the past? This reaction can happen in less than a minute. I have HCl in the lab. I have zinc chloride in the lab. I take a few drops of the alcohol, a few drops of the chloride, done. I can be like, that is a tertiary alcohol. So in a matter of seconds, I have structural information. Okay? And relatively cheaply. Okay? Do I know which tertiary alcohol it is? No. So I still have a lot more work to do, but I have some idea of the chemistry behind it. Why is it becoming less common now? Spectroscopy is becoming cheaper and cheaper and cheaper. It's still not at that same price point, but it's cheap enough that even institutions like us can get an NMR. So now in 2 minutes, I can get the entire structure of the compound as opposed to just knowing it's an alcohol. Okay? So depending on who writes the ACS test at that particular sequence in time, you may see questions based off classification. Why? Because the person writing the test was or is old. Okay? If the people writing the test are younger, they're not going to push to the classification test because we have better techniques. Okay? Because we don't know, you got to know everything. Make sense? Okay. So, complications behind these. What does it look like happened with the first one?
Substitution?
Yeah, it's a substitution. Is it just a normal substitution?
No.
No. Why not?
Hydroid shift.
Look at where the chemistry is. Okay? That carbon should be our electrophilic carbon. We add the acid to make water a good leaving group. Fantastic. Where should the bromide go? Right there. Not what it did. Why not? We have to remember that in these reactions, what do I form? Carbocations. The instant you form a carbocation, what should you be thinking? Rearrangement. Could I rearrange a secondary carbocation to a more stable place? Yes, I could go to tertiary. That's why the bromide comes in. So if you see carbocations, which is what you were talking about earlier when we were talking, yes, you should be thinking about rearrangements. If you don't have a carbocation, don't do it. Did anybody see the carbocation written up there? No. This is an awesome question that trips up lots of students who do what? Memorize. Because now they don't know the mechanism, they don't know a carbocation forms, they don't know the rearrangement happens. Okay? This is why you have to have a balance of that content. Make sense? Okay. How fast would we expect that second one to occur?
Very quickly.
Super quick because a primary carbocation is exceptionally stable. Remember, this is the Lucas test. Super quick if it is tertiary alcohol. As a primary alcohol, that is a very slow reaction. Does it happen? Yes. Okay, but it is a very slow reaction. The next one, what makes it tricky? Okay, the sulfate. So we'd be doing an elimination instead of a nucleophilic substitution. What else? Where would you expect the pi bond to form? Where's your leaving group? At the end, which would mean, shouldn't we remove the hydrogen from there?
That's a carbocation.
Okay. The carbocation would still theoretically form out here. With the concentrations, it will shift. Okay. It sucks. It takes time. It's something you got to watch out for. Last one. Okay. Notice it doesn't say dilute. Okay. Sometimes the concentration is specified, sometimes it's not. I do try to specify it to be extra clear. Make sense? Okay. I really wanted to at least talk about this slide. I know we're a little bit over. Please hold with me. These ones are now a little bit weirder. Okay. Why might these be weirder?
They're maintaining.
Have you done acid-base reactions before?
Yes.
Yes, that was literally all of Gen Chem was acid-base. You've done lots and lots of acid-base. We just talked about all the acid-base reactions. These all become weird because they're not strict acid-base reactions. They become much more challenging because they aren't dealing with that same familiar chemistry. What else makes them more challenging? Notice all of these have stereochemistry. That stereochemistry is a direct result of the mechanisms behind them. Okay? We will address those mechanisms and a little bit more on Monday, but just to kind of think about it, which mechanism do you think you're going to run through? So first, substitution or elimination? Substitution. Why? I'll accept at the top. What else? There's no pi bonds in your product. Should it be SN1 or SN2?
SN2.
SN2. Virtually all of these mechanisms, when the chemistry occurs at the carbon, you're doing an SN2 reaction.
Is that because you're doing backside?
You are doing backside attack. That results in a stereochemically pure product. SN1 forms a carbocation. You get two products. Okay, that's why the SN1s, we didn't talk about stereochemistry. We couldn't really evaluate it. Here we can. Okay, because backside attack was mentioned. Let's take a look here. Is that a backside attack? Yes. Faster responses mean we get done faster. Okay, this one.
No.
Yes.
Same side.
No, it's not. It didn't attack the carbon. It attacked the oxygen.
Nothing happened to the carbon. This one becomes tricky, and everybody goes, oh, well, it's retention of stereochemistry. It's not actually retention or loss. Nothing happened to the carbon. The oxygen reacted with that species to produce this. Stereochemistry is not changing, it's not affected. So it's a bad question to ask. It's not backside attack or retention. It is. Okay? This one.
That would be a backside attack.
It inverted, right? Backside attack.
Yeah.
Top one.
Not a backside attack.
Not a backside attack. What's extra weird?
You're using the same reagent. You're not.
The exact same freaking reagent and I get retention or inversion? Yes, that makes this reagent tricky and it all zeroes in on that PYR. That makes it very, very challenging. Okay, it is one that is not consistently referenced very well. It is one that I very carefully watch in all of our standardized tests, and I watch it in our tests too. Okay, because it makes a huge difference in the end result on what that solvent is. Okay, we will talk about those details on Monday. Be ready to see the end of these and then talk about synthesis as a breakdown. The exam is Wednesday. We're borderline on content. Okay, so we're going to look at details of these, which isn't sort of officially new content, sort of. And then I think we'll touch on a couple other slides just to say, like, you've seen these things before, but I won't push them or test them heavily. Okay?